so we're going to be talking about two different things within this one lesson. One of them is continuity and the other one is one-sided limits. So let's start with what continuous means. Okay, so continuous means that there's a function that is unbroken. You can draw it without picking up your pencil at a particular point. Okay, at a particular point. That means that there's no hole, right? And you've seen functions that have holes in them. You've seen jumps. This one has no jumps and there's no particular forms of gap. Okay, so that's what a continuous function looks like. Now there's different types of discontinuities. Okay, there are some that are called removable, okay, which is also known as a hole. You can see one of those here, right? There's a hole, all right? It's a point discontinuity. There's just one itty bitty little point where the function's acting funky. And notice like that there is another, for this one anyway, the function is defined there. It's just not what you think it might be. All right, and then there are non-removable discontinuities. So those are either jumps or infinite. So this first one that you're looking at here, this is a jump discontinuity, whereas this last one that has a vertical asymptote, this is considered to be an infinite discontinuity. All right, so now here are some requirements for continuity. Okay, the first one says that the function is defined. Okay, that means that there is some sort of a value for the function when you plug c in. Okay, the second thing is saying that the limit as you are approaching that c value also exists. Okay, now this is what seems kind of weird. This is saying that those two things are equal. Okay, now if you're wondering, well, how could they not be equal? Let's go back to this picture that we looked at here. Okay, so I'm looking at, let me highlight it for you. I'm looking at this picture. Okay, so is the function defined here? Yes, yes it is. There, I know what the function equals right there. Okay, does the limit exist as we are approaching? Yes, right? I am approaching this point. So then the question is, do those two things equal each other? Well, no, they don't. They do not at all. And so that's why this is not continuous. Okay, so that being said, this says find the x values, if any, at which f is not continuous. This is going to sort of depend on you remembering at least even vaguely what these pictures look like. Okay, I'm not saying you have to be able to draw a perfectly accurate graph, but this one, all right, I'm hoping based on the fact that you have an x in the denominator that you know that there is an asymptote right here where x equals 0. Okay, I'm also hoping that you remember, and if not, maybe you're plugging in a couple x values, that this graph looks like this. Okay, so it is discontinuous at x equals 0, and the kind of discontinuity is infinite. Okay, let's try another. Okay, so on this one, and again, I know it's been a while since we did rational functions, but I'm hoping you remember to factor this thing. And because there's a common factor, right, this thing has a hole. And the hole is where x is equal to -2. Okay, now holes are considered to be point discontinuities. Okay, that is a point discontinuity. Okay, this function, and because of COVID, we haven't really graphed these very much, but you've definitely seen a picture of cosine. It looks like this. Oh, well, let's try that again. It looks like this. That's what cosine looks like. All right, there's no jumps, there's no holes, there's no gaps, there's nothing. This thing is just continuous. Okay, this next one. You may not remember this one. I'm not sure how much we covered this earlier, but if you went to Desmos, let's say, and you graphed this, it would look like this. Give me just a sec. At 1, 2, 3, you'd have a line that looks like this and a line that looks like this. Okay, so just again, based on the picture, this is a jump discontinuity, and it occurs when x equals 3. Okay, so again, this is where it occurs, and this is the kind of discontinuity. Okay, so now we're going to jump, sorry, discontinuity joke. Anyway, we're going to switch. How about that? We're going to switch to the one-sided limit part of this. Okay, so you've seen functions that look like this before. This is a piecewise function. All right, and if you really wanted to graph it, you could, right? This is just one line, and this is a completely different line, and this one, the top one occurs when x is less than 2, and the bottom one occurs when x is greater than 2. You can graph it if you want. What this question's asking, though, is if you're approaching 2 from the right, 2 from the right would mean numbers that are greater than 2, right? So these numbers, what is x approaching? Okay, so if I put 2 in here, I get 3. Okay, again, you have to figure out, are we coming from the left or the right? Where should I plug this thing in? Okay, this next one, if you remember, is called the greatest integer function. If you don't remember what that looks like, my suggestion is get onto Desmos, type the thing in so you know what it looks like, and you'll be able to look at 2, right? You're approaching 2 from the left, and you'll see that you have an answer of -4. Okay. Let's see, for this one, again, I'm not sure if you remember graphing these, but just a quick little sketch. Hopefully you remember that it looks something like this when x equals 2, like this and like that. This is up at 1, by the way, and this is down at -1. Anyway, so here, if I'm approaching 2, right, I'm approaching 2 from the right, you can see that this equals 1, all right? The one-sided limit, right? Again, I'm approaching 2 from the right. Now, notice how this is different than this one, okay? Again, same picture, right? It's the same picture, 1, 2, 1. Okay, same picture. But notice this is asking for the limit as x is approaching 2. That means that the limit from the left and the limit from the right, sorry, and I know I did those backwards. This is from the left, this is from the right. Those have to equal the same number. This particular limit does not exist.